Hello guys, how are you doing? In the last video, we talked about the universal law of gravitation given by Isaac Newton. He said that gravitational force is a mutually attractive force that acts between any two objects possessing mass. Now, the magnitude of gravitational force is given by F is equal to G times m1 m2 divided by r square, where capital G here is the gravitational constant, m1 and m2 are the masses of two objects involved, and r is the separation or the distance between them. Now, as I said in the last video, Newton didn't come up with this formula all by himself. He was inspired by the work of one of his predecessors called Johannes Kepler, who by the way was a great scientist himself. Johannes Kepler observed the motion of the planets in the night sky using his telescope for several years. Now, all the observations that he collected in that long term revealed several secrets about the motion of the planets themselves. Now, based on that, Kepler came up with his own 3 laws of planetary motion, which by the way also had the secrets of the universal law of gravitation hidden in them. Isaac Newton, after a generation, found out Kepler's work and also found out those hints that revealed the universal law of gravitation to him. So in today's video, we'll see what those 3 laws of planetary motion were and what were those hints hidden in them that Newton found out later and formulated the theory of universal gravitation. So without further ado, let's begin, guys. So guys, let's begin by talking about the 3 laws of planetary motion given by Kepler. The first law says that the orbit of a planet is an ellipse with sun present at one of its foci. The second law says that as a planet goes around, the line joining the sun and the planet sweeps equal areas in equal intervals of time. Finally, the third law says that the cube of the mean distance between the sun and the planet, small r, is directly proportional to the square of the orbital period of the planet, capital T. So the third law says that r cube is proportional to t square. Now, I'm sure most of you are confused about each of these 3 laws as they contain terms that you have never heard before. So, let's begin by talking about each law one by one and try understanding what they really want to say. So guys, I'm sure all of you know that this is a circle. It has a fixed center and all the points present on its body are at an equal distance from the center, and that distance is nothing but the radius of the circle. Now, this shape over here is an ellipse. You can think of it as a squished circle. Many people can relate to it when I say it looks similar to a rugby ball or even an egg. Now, due to its shape, an ellipse does not have a center like a circle does. Instead, it has 2 unique foci, one focus on the left and the other focus on the right. Now, Kepler's first law says that the orbit or the path of a planet going around the sun actually looks like an ellipse and not a circle. Now, because the orbit of a planet is not circular, the sun can't be present at the center. So, if a planet goes around in an elliptical path, where do you think is the sun present? Well, the first law of planetary motion tells us that sun is present at one of the 2 foci of the ellipse. So if we assume this as the path of our own planet Earth around the sun, then the position of the sun would be at either the left focus or the right focus. It can be either of them because left and right is just a matter of perspective from where you are observing. So guys, the first law essentially tells us the shape of the orbit of a planet and also the position of the sun. But the second law describes how a planet moves in its own orbit, whether it moves at a constant speed or it moves at a variable speed. Now, to understand the second law, we need to draw a line joining the planet and the sun. Now, as a planet goes around in its orbit, you can see that this straight line traces a certain amount of area within the ellipse. Now, Kepler's second law essentially tells us that in equal intervals of time, this straight line would cover or would trace equal amounts of area. For example, take a look at our planet Earth orbiting around the sun. Now, as the Earth moves, you can see that the line joining the Earth and the sun traverses a certain amount of area. Now, we know that Earth takes 12 months of time to complete one revolution around the sun. So if we divide that 12-month time into 4 equal intervals, each 3 months long, then the area traversed corresponding to each of those intervals can be shown like this. Now, Kepler's second law says that the line joining a planet and the sun traverses equal areas in equal intervals of time. So this means that the 4 sections that we have highlighted over here have equal areas because each of those sections have been traversed in equal intervals of time. Fascinating, isn't it? Now, we can derive another fascinating conclusion from Kepler's second law. So notice that in the same time interval, Earth travels a longer distance when it's closer to the sun and a shorter distance when it's farther away from the sun. So if an object travels more distance in the same time, then it's basically moving at a faster speed, right? So we can say that Earth moves at a faster speed when it's closer to the sun and at a slower speed when it's farther away from the sun. Now, if you notice the path or the trajectories of other planets as well, the same is true for them. So this tells us that all planets move faster when they are closer to the sun and slower when they are farther away. Now, this also means that all planets travel at variable speeds throughout their orbit and not at a fixed speed. Keep that in mind. Great! Now, Kepler's third law gives us a mathematical relationship between the mean radius and the orbital period. Now, the question is, what do we mean by these terms? Mean radius is the average radius of any planet taken from the sun. As an example, I have calculated the mean radius of Earth over here. You can see that I have marked 2 separate distances on the entire trajectory of planet Earth taken from the sun. R1 is the shortest distance between the sun and the Earth, and R2 is the longest distance between the sun and the Earth. Now, mean radius is nothing but the average of these 2 distances. So the mean radius for Earth is nothing but R1 plus R2 divided by 2. The same thing applies for other planets as well. Now, in a completely different way, we can think of mean radius as the radius of an imaginary circle around the sun in which the planet is presumed to be moving. So using the concept of mean radius, we essentially average out the elliptical path into a circular path. Now that's another fascinating thing. Now, according to Kepler's third law, r cube is proportional to t square, where r is the mean radius and t is the orbital period. Now, of course, orbital period is the time taken by a planet to complete one revolution around the sun. For our planet Earth, the orbital period is equal to 12 months. So guys, as far as the 3 laws of planetary motion are concerned, we are done here. But as it turns out, the Kepler's third law essentially holds secrets for the universal law of gravitation as well. Now, Kepler himself couldn't find it, but his successor, Isaac Newton, a generation later, was able to do so. So let's go ahead and see how Newton formulated his argument about the universal law of gravitation using the Kepler's third law. So guys, when an object undergoes a uniform circular motion, 2 important relationships hold true for it. The first one is that force acting on the object F is proportional to v square by r. Now v over here is the constant speed of the object and r is the radius of the circle in which the object is moving. The second relationship that holds true over here is v proportional to r divided by t, where v once again is the speed of the object, r is the radius of the circle, and capital T is the orbital period. Now, the first relationship comes from the equation of centripetal force that you will learn about in your higher standards, so ignore that for now. But the second relationship essentially comes from the formula speed is equal to distance upon time, which I'm sure all of you are familiar with. So now that you're clear about this, we can go ahead and talk about Newton's argument. So Newton said that instead of planets going around in elliptical paths at variable speeds, let's imagine planets going around in a circular path of mean radius r at constant speeds. Now the moment we do that, the 2 equations or the 2 proportionalities we just discussed are directly applicable to them. Now on top of that, there is one more relationship that is applicable to them, which is r cube proportional to t square, the relationship coming from Kepler's third law itself. So now Newton had 3 proportionalities to play with, and he had to establish a relationship between the force F and the mean radius r. Now, why was Newton so interested in just these 2 quantities? Well, you see, because Newton thought that the force of gravitational attraction was the only force responsible for keeping a planet in a closed path around the sun. So, in Newton's mind, force F was the force of gravitation itself. And if he was able to establish a relationship between F and the mean radius r, he could come up with a general formula of gravitational force itself. And that's what Newton did. He did a series of calculations to obtain the relationship between F and r as F proportional to 1 by r square. Now, from this relationship, Newton understood that the force of gravity acting between any two objects was inversely proportional to the square of separation between them. So, if the objects were close together, the force of gravity acting between them was high. But if the objects were placed far apart, the force of gravity acting between them was low. On top of that, Newton was also able to figure out that the force of gravitation was directly proportional to the product of the masses involved. He was able to say this by looking at heavy celestial bodies, which exerted considerable gravitational force as compared to the lighter celestial bodies, which exerted less or weaker gravitational forces. So guys, that's it for today. I hope you had a good time learning about the three laws of planetary motion given by Johannes Kepler, and also how Isaac Newton inferred the universal law of gravitation from Kepler's third law. In the next video, we'll solve some problems based on the universal law of gravitation. For now, let's summarize whatever we have learned so far. Kepler's first law says that the orbit of a planet is an ellipse with sun present at one of the two foci. Kepler's second law says that the line joining a planet and the sun sweeps equal areas in equal intervals of time. Kepler's third law says that the cube of the mean radius of a planet is directly proportional to the square of its orbital period.